at the edge of a universe humming a tune. For merely dreaming we were snow.
Hello, my name is Max Akerman, and this video will focus on radio astronomy, looking at how astronomers use radio waves to observe the universe, the technology behind radio telescopes, and discoveries made using radio technology. When we look up at the night sky, we usually think of stars, planets, and galaxies as things we see with our eyes or through optical telescopes. But the universe is not only visible, it is also audible in a scientific sense. Objects in space emit energy across the entire electromagnetic spectrum, including radio waves, which are invisible to humans. Radio astronomy is the branch of astronomy that studies these radio signals from space to uncover information about celestial objects and cosmic events that cannot be detected using visible light alone. Radio astronomy differs from optical astronomy primarily in the type of electromagnetic radiation each one studies, and the kind of information that radiation can reveal. Optical astronomy focuses on visible light, which has a relatively short wavelength, and is a small portion of the electromagnetic spectrum that human eyes can naturally detect. Because it relies on visible light, optical astronomy is limited by conditions such as daylight, cloud cover, and dust or gas in space that can block or scatter light before it reaches Earth. Radio astronomy, on the other hand, studies radio waves, which have much longer wavelengths and lower frequencies than visible light. These radio emissions are produced by a wide variety of cosmic sources, including stars, galaxies, nebulae, pulsars, and the remnants of supernova explosions. One major advantage of radio waves is their ability to pass through interstellar dust and gas that would otherwise obscure objects in an optical observation. This allows astronomers to observe regions such as the center of the Milky Way or dense star-forming clouds that are nearly invisible in visible light. Another important difference is how the data is collected and interpreted. Optical telescopes form images that look similar to photographs, while radio telescopes gather signals that are often translated into graphs, intensity maps, or false color images through computer processing. In this sense, optical astronomy is more like seeing the universe, whereas radio astronomy is more like listening to it, detecting patterns and signals that reveal physical properties such as temperature, motion, chemical composition, and magnetic fields that cannot be easily measured with visible light alone. Radio telescopes function very differently from the telescopes we typically imagine. Instead of mirrors or lenses that focus visible light, radio telescopes use large dish-shaped metal antennas to collect radio signals coming from space. These dishes are often made of reflective metal panels that bounce incoming radio waves towards a central focal point, similar in the principle to how a satellite dish collects television signals. The reason these antennas must be so large, sometimes stretching tens or even hundreds of meters wide, is because radio waves have very long wavelengths compared to visible light. Longer wavelengths are harder to capture precisely, so a bigger collecting surface is needed to gather enough signal strength and detail. A larger dish also increases the telescope's sensitivity, meaning it can detect extremely faint radio emissions from distant galaxies or weak cosmic background signals that would otherwise be lost in noise. Once the dish collects the radio waves, the signals are directed to a receiver, usually located at the focal point above the dish. The receiver is cooled to very low temperatures to reduce electronic noise, because radio signals from space are incredibly faint compared to interference from Earth-based sources such as phones, satellites, or even car engines. The receiver amplifies the signal and converts it into electrical data that computers can analyze. Since radio waves are not images in the traditional sense, the data is instead processed into intensity maps and graphs that represent different frequencies and strengths in radiation. This allows astronomers to identify chemical elements, motion through Doppler shifts, temperature variations, and magnetic field structures. Some radio observatories take this a step further by linking multiple dishes together in a technique called interferometry. Interferometry works by synchronizing several telescopes that are spread out over large distances, sometimes across entire countries or even continents. Each dish observes the same object at the same time, and the computers combine their signals with extremely precise timing using atomic clocks. The reason this increases resolution is because the effective size of a telescope determines how much detail it can see. A single dish might be 50 meters wide, but if you connect two dishes that are 5 kilometers apart, the system behaves like a telescope that is 5 kilometers wide. The greater the distance between dishes, called the baseline, the finer the detail astronomers can resolve. This is why interferometry can produce incredibly sharp images of distant galaxies or black hole environments, far sharper than any single radio dish could ever achieve on its own. Radio astronomy allows scientists to study a wide range of cosmic phenomena because many objects in space naturally emit strong radio signals or are hidden behind dust that blocks visible light. Some of the most commonly studied objects include pulsars, which are rapidly rotating neutron stars that emit periodic radio signals. Pulsars are formed when massive stars collapse after a supernova, compressing their cores into incredibly dense spheres only about 20 kilometers wide. As they spin, beams of radio energy sweep across space like lighthouse beams. When those beams pass Earth, astronomers detect them as pulses. These pulses are so precise that pulsars are sometimes used as cosmic clocks to test theories of gravity and even to search for gravitational waves. Another commonly studied object are interstellar gas clouds, which are regions where new stars are formed. These clouds are made mostly of hydrogen gas and are often cold and dense, making them nearly invisible in optical light. Radio astronomy can detect the specific radio frequencies emitted by hydrogen atoms, allowing astronomers to map the structure and motion of these clouds. This helps scientists understand star formation, chemical composition, and how galaxies evolve over time. Radio astronomy has led to several groundbreaking discoveries that completely changed how scientists understand the universe. One of the most significant was the detection of cosmic microwave background radiation in the 1960s. This radiation is an extremely faint, uniform glow that fills all of space and can be detected with radio equipment. Its discovery provided strong evidence for the Big Bang theory because it matched predictions that the early universe would have left behind a measurable heat signature as it expanded and cooled. By studying tiny temperature variations in this radiation, astronomers have been able to estimate the age of the universe, its rate of expansion, and the proportions of matter and energy it contains. More recent research has used radio astronomy to better understand galaxy formation, black holes, and the distribution of dark matter. Radio telescopes can observe jets of energy emitted from supermassive black holes at the centers of galaxies, helping scientists analyze how these black holes influence the growth and their structure of the host galaxies. Large radio surveys also allow astronomers to map the movement of hydrogen gas across vast distances, which reveals how galaxies merge, rotate, and evolve over billions of years. Although dark matter itself cannot be detected directly, radio observations help measure its gravitational effects by tracking how visible matter moves within galaxies and galaxy clusters. Radio astronomy plays a critical role in mapping the structure and composition of the universe. By observing hydrogen gas, which is the most abundant element in space, astronomers can trace the spiral arms of galaxies and analyze how galaxies rotate and interact. Hydrogen is especially useful because it naturally emits a very specific radio signal known as the 21 centimeter line. This signal is produced when the electron in a hydrogen atom changes its energy state and releases a tiny burst of radio energy. Even though each individual atom emits a very weak signal, hydrogen is so common throughout the universe that when observed in massive clouds, the combined signal becomes strong enough for radio telescopes to detect. In addition, radio waves usually do not carry enough energy to strongly excite atoms or molecules, meaning they interact less with matter and can move across space with minimal interference. This is why radio telescopes can observe regions such as the center of the Milky Way or dense star-forming nebulae that appear dark or hidden in optical images. Radio observations also help scientists examine magnetic fields, galactic collisions, and the distribution of matter on a cosmic scale. Hydrogen acts almost like a universal tracer or reference marker, giving astronomers a consistent signal that can be detected across enormous distances. Since nearly every galaxy contains vast amounts of hydrogen, studying its radio emissions offers a reliable and standardized way to compare galaxies and understand how matter is arranged throughout the universe. In short, hydrogen is central to radio astronomy because it is abundant, detectable, and able to penetrate cosmic dust, and extremely informative about large-scale structure. Radio astronomy expands our perception of the universe beyond by what we can see. By capturing invisible radio waves, scientists can uncover hidden regions of space, study extreme cosmic events, and explore the origins and structure of the cosmos itself. In many ways, radio astronomy is like giving humanity a new sense, the ability to listen to the universe and learn its deepest secrets.
It's now and never.